The air all around us, it's a total paradox, right? On one hand, it's this cozy blanket that keeps us alive. But on the other, it's this fiery wall, ready to torch anything that tries to punch through from space. So today, let's get into that. We're going to look at both sides of our atmosphere, the gentle guardian and the violent gatekeeper. Okay, so to really wrap your head around just how crucial our atmosphere is, all you gotta do is look up at the moon. Seriously. With nothing to protect it, the moon is just a world of insane extremes. We're talking hot enough to boil water during the day, and then at night, bam, colder than liquid nitrogen. Can you even imagine that? That thin layer of air around us is literally the only thing standing between us and that kind of chaos. All right, so first things first, let's talk about this incredible atmospheric blanket we're all living under. I mean, what is this invisible shield actually made of? And how in the world does it pull off this magic trick of keeping our planet's temperature, just right for us? So, take a look at this. It's pretty wild. The air we're breathing right now, it's pretty much all nitrogen and oxygen. But see that tiny little sliver, that 1%? That's where the real action is. The key to, well, everything is hiding right there. Those are the gases that basically work as the thermostat for the whole planet. Yeah, that little 1% is where you find what we call greenhouse gases. And I know you've heard that term a million times, but the core idea is super simple. They're just gases that are really, really good at trapping heat. The big ones are water vapor and carbon dioxide. And here's the thing, we absolutely need them. Without them, Earth would just be a giant frozen ice ball, a total wasteland. And here's how it all works. It's actually a pretty elegant two-step process. First, sunlight, which is shortwave radiation, zips right through the atmosphere and warms up the Earth. Easy enough. But then, when the Earth tries to send that heat back out into space as long-wave radiation, well, that's when those greenhouse gases step in. They absorb it, they trap it, keeping that warmth in. It's just like the glass on a greenhouse, right? Super simple idea, but it's the very thing that makes this planet habitable. Okay, so you might be thinking, wait, if water vapor is the most common one, why is everyone always talking about carbon dioxide? And that's a great question. The answer is CO2 is just incredibly stubborn. It's got serious staying power. Once it gets up into the atmosphere, it hangs around for hundreds of years, just trapping heat day in, day out. And that's why even a seemingly small change in CO2 levels can have such a massive long-term impact. So, we've seen how the atmosphere acts like this gentle, protective blanket. But what happens when we try to come at it from the other direction, from space? Well, that's when our cozy blanket turns into a raging inferno. Let's get into it. Okay, I want you to picture this. You've got a crew of astronauts in their capsule, think something like a SpaceX Crew Dragon, and they're coming home. They are just about to hit the very top layer of the atmosphere. And in doing so, they're starting what is easily the most dangerous few minutes of their entire trip. And they're not just entering the atmosphere. No, they are slamming into it. We're talking about 8,000 meters per second. That's almost 5 miles every single second. At that kind of speed, the air in front of you, no matter how thin it seems, basically becomes a solid brick wall. Yeah, so what happens when you hit that wall of air at something like 25 times the speed of sound? Well, the air molecules literally can't get out of the way fast enough. They just pile up and compress violently, creating this massive shockwave. It's a wave of pressure so powerful it would rip a normal airplane to shreds in an instant. And the pressure gets so intense, so extreme, that it actually rips the oxygen and nitrogen molecules in the air apart. It's just tearing them to pieces. And when that happens, a ton of energy is released. All that energy creates this glowing bubble of plasma that surrounds the capsule. A bubble that gets hotter than the surface of the sun. Just incredible. Now, this superheated plasma has a really weird side effect. It blocks all radio communications. So for a few minutes, what must feel like an eternity for everyone at Mission Control, there is just silence. It's called the re-entry blackout. They can't talk to the crew. The crew can't talk to them. All they can do is stare at their screens and just hope that everything is going okay inside that fireball. Okay, so that's the danger of coming in from the outside. But what happens when you're already way up high, inside the atmosphere, say in an airplane, and your little pressurized bubble of air suddenly disappears? What happens when that bubble bursts? Well, it turns out there are a few different ways this can go down, and none of them are good. You've got explosive decompression, which happens in less than half a second, so fast your lungs can't even keep up. Then there's rapid decompression, which is a bit slower but still incredibly dangerous. And then you've got the really sneaky one, gradual decompression. It can happen so slowly that no one even notices until it's too late. And the force you're dealing with here is just staggering. There's this quote from a NASA scientist, Jeffrey A. Landis, that really paints a picture. He said, "Anyone blocking the hole would have half a ton of force pushing them towards it." Think about that. Half a ton. This isn't just a little bit of wind. It's a powerful, violent force. But honestly, as scary as getting sucked out of a plane sounds, that explosive force isn't even the number one threat. The real killer, the primary danger, is hypoxia. That's a lack of oxygen getting to your brain. See, at a typical cruising altitude, you have maybe 30 seconds of useful consciousness. That's it. After that, your brain just starts to shut down. And of course, there are other nasty things too, like barotrauma, where the sudden pressure change can do serious damage to your body. So, when you're faced with these kinds of extreme challenges, fiery reentry on one side, explosive decompression on the other, you've got to get creative. It has pushed our engineering to the absolute limit. We've had to come up with some truly incredible solutions just to build shields against our own sky. I mean, look at how we've learned to deal with the heat of reentry. Back in the Apollo days, it was all about using heavy materials to just soak up the heat. Then the space shuttle came along with its reusable insulating tiles, which was a huge leap. Today, modern capsules use something called ablative shields. These are layers that are literally designed to burn away, carrying the heat away with them. And the future? We might see stuff like transpiration cooling, where the spacecraft basically sweats a coolant to keep from overheating. Wild stuff. And it's the same for airplanes. To make sure a small hole doesn't just rip the whole plane apart, modern aircraft are built with these reinforcing ribs all along the fuselage. They act like ripstops. And the doors are super clever. They're what's called plug doors, which means they're shaped so that the pressure inside the cabin actually pushes them tighter against the frame. The higher you go, the more secure the seal becomes. It's brilliant. So this really sums it all up, doesn't it? For every single atmospheric challenge, we've had to come up with an equally clever engineering solution. Whether it's the extreme heat of reentry, the pressure loss at high altitude, or even just how the planet naturally traps radiation, for every problem, there's a solution, either engineered or natural. It's a constant battle between us and the sky. So what's the big takeaway here? It's this profound duality, right? Our atmosphere is this incredibly fragile shield that we absolutely have to protect. But at the same time, it's a violent barrier we have to constantly figure out how to overcome. And that leaves us with a pretty big question. For you, for all of us. As we keep pushing further out into space, and as we keep changing the makeup of the atmosphere right here on Earth, how is our relationship with this blanket, this barrier, this battlefield, how is that going to change?